Okay, we're going to take a look at exponential functions. Exponentials and logarithmic functions, these are inverse functions, and we'll see that as we work through this section, which we just finished talking about inverse functions in our previous section. With that said, an exponential function is a function of the form a to the power of x, where a is a base whose restriction is a must be greater than 0, so a number greater than 0, can't be negative, must be positive, and it cannot equal 1. Right? We can't have 1. Now, if we were to have a base of 1, right, we would have a horizontal line. Y equal 1 to any power is 1, right? So y equal 1 is a constant function. This is an exponential function, a function that increases or decreases exponentially. Some examples of some exponential functions. We've got a function here of 3 to the x power. Our base a is 3. Our domain variable, our input variable, is up here in the exponent, right? This is an exponential model. Here in g of x, we've got a base 5 exponential. There's our number. Base a is greater than 0. It's not equal to 1. Up here in the exponent contains our input or our domain variable, x to minus 2 power. You can see here base 7 exponential raised to the power of x squared minus 4x. I want to talk about the characteristics of its graph. It says characteristics of a graph of function a to the x power, where our base is greater than 1. It says we have a domain of all real numbers x. So again, that means no undefined values with an exponential. We plug anything we want into x, we'll get an output. Now our outputs, our range, right, the y values, remember domain is x and range is y. Our outputs are going to be positive values. They're going to be positive outputs. Y values are all y values greater than 0. You can see given by this interval of 0 to infinity with the parentheses on 0. All right, our y-intercept point, which would be an easy point to find, it says if we let x be 0, which is how we find a y-intercept. Remember, y-intercepts are when we take our function and plug in 0 for x. F of 0 would be a to the 0 power. Yeah, if we raise it to a power of 0, this number a that is greater than 0, not equal 1, we know raising that number to a power of 0 is going to always give us an output of 1. So yeah, the y-intercept point is the point 0, 1. So we know graphically our exponential model will pass through the y-axis at 0, 1. All right. We also know that this function of a to the x, where a is greater than 1, is a function that increases for all x. It's always increasing. So with that said, it's a 1-to-1 function, right? If you remember back to our previous section that we lectured with inverse functions, it must be 1-to-1, all right? And it must be that each y gives exactly 1x, and it must always increase or decrease. And it says here that this model is always increasing, so therefore it would be 1-to-1. And it's a continuous function, right? It's no undefined values. With that said, it has an asymptote. So it says here the line y equals 0 is the horizontal asymptote. So what will happen with our graph is it'll flatten out horizontally as we approach the x-axis. So remember, horizontal asymptotes are lines that shape our graph. So with that said, let's go ahead and look at over here on the side a sketch of a to the x, where a is greater than 1. So I'm going to do that. I'm going to put it in blue, different color. So we've noticed we were given a horizontal asymptote here at the x-axis. I'm going to go ahead and draw that in here. So y equals 0 is our horizontal asymptote. We have a y-intercept at the point 0, 1. All right. Now with this horizontal asymptote, it will never touch it. We said the range will be all values greater than 0, never equals 0. So again, it will get closer and closer and closer to 0, but never touch it. But if it's going to be increasing for all x, this is coming from negative infinity, it's going to be coming from the x-axis, the horizontal asymptote. Always rising, always going up and increasing in value. So here's our exponential model. So here's f of x equal to a to the x power, where a is greater than 1. So you see domain, graph covers the x-axis, all real numbers. covers the y-axis from 0 to infinity, right? You see your range values covered on the positive side of the y-axis, right? Right here is our range, right in here. And again, our domain is all these x values. So you see our graph there of the function a to the x. Well, now I want to look at another case. All right, we're going to look at what happens with functions of the form a to the x, where a is greater than 0 but less than 1. So there we said a must be greater than 1. Well, what happens when our base is less than 1 but greater than 0, which is a possibility, right? With exponential models, remember, a must be greater than 0. Just can't equal 1. So if we have a base like 1/2 or 2/3 or 3/4, right, those are numbers that are greater than 0 and less than 1. So it says a to the x where a is greater than 0 and less than 1. And it says the domain is all real numbers x, and the range is all positive values of y, same as we had with a to the x where a is greater than 1. And of course, y-intercept is 0, 1. If we plug in 0 for x, we get an output of 1. Here's where we're different. Instead of increasing for all x, it decreases for all x values. So in our graph, let's put it in a different color. And we'll put it here in red. So our y-intercept at 0, 1, right? Horizontal asymptote here at the x-axis at y equals 0, right? As we look at that graph, it's always decreasing. It's always decreasing in value as we move from left to right on this graph. All right, here's the graph of a to the x, where a is a number greater than 0 but less than 1. So a is between 0 and 1 with that graph in red, which if you notice is a reflection of this graph here in blue across the y-axis, right? These are mirror images across the y-axis. So this would also be the graph of a to the negative x, where a is greater than 1. So I'll put that up here. We know from transformations, if we multiply x by negative, we flip our graph across the x-axis. So yeah, we had a negative exponent and our base is greater than 1. We would be decreasing in value, right? It would decrease exponentially. So you can see again your characteristics, of course, continuous, 1 to 1, those key characteristics. So that's our exponential model, right? Increasing or decreasing exponentially. It says down here to graph the following exponential functions using some transformations if you need to. State the asymptote, the domain, and the range of these graphs. All right, well, let's start with example A. So example A, I'm going to go ahead and build in my x and my y-axis. We know the graph of 4 to the x power. Well, the graph of 4 to the x, right, has a y-intercept at 0, 1, right? We know 4 to the 0 power is 1, right? F of 0 is 1. Again, this is a graph of the form a to the x power, where a is greater than 1. So we have a horizontal asymptote, right? We know our graph will flatten out at the x-axis. So if we want, we'll show that here in blue. So here y equal to 0, horizontal asymptote. And then again, increasing for all values of x. So it increases exponentially, base 4. So as we draw in a sketch of this graph, right, there we are with our graph. Now we could put in some other points, right? We could look at, for example, that's f of 0 is 1. What would f of 1 be, right? F of 1 would be 4, right? You plug in 1 for x, 4 to the 1 power is 4. So you would get the ordered pair of 1, 4. So you could plot as many points as you want, make a table, right, of values, is increasing exponentially. And you put in 2, 2, 16, for example, 4 squared, 16, and so forth, right? And you can put in some negative values, right? Put in negative 1, you get 4 to negative 1 power, 1/4. But again, that's a quick sketch, just showing our graph there of 4 to the x power. Now, as we look at example B, we have a base of 1/4. So here's a function, and we'll put this one in a different color. Right, in this function, we've got a function of the form a to the x, but this time we have a being greater than 0, but less than 1. So what happens graphically is it decreases for all x values. So as we're going to look at our graph of this exponential, right, we could go ahead and graph that in here, right? And as you look at this y-intercept point, let's go ahead and put it in blue. We know 1/4 to the 0 power is 1, so we know it passes through 0, 1. We know it's going to flatten out. We know the horizontal asymptote, right, is y equal to 0, the x-axis. And again, since the base is less than 1, instead of increasing, it decreases in value. So as we go to infinity, right, we get smaller and smaller in value, but it will never touch the x-axis. Our range is all numbers greater than 0. But there's a sketch, right, of 1/4 to the x power. Now, with that said, you could have rewritten this function. I want to show you this. Back on this other example, we also know that 1/4 to the x power, well, you could take 1/4 and get rid of the fraction, right? We could flip 4 up to the numerator by changing the sign of the exponent, right? This would be the same thing as saying 4 to the negative 1 power raised to the x. And we know from exponent properties that a power to a power, you multiply the exponents, and you get 4 to the negative x power. And if you remember, this negative, right, that's up here with the domain variable, that means we would reflect, right, the graph of 4 to the x, which we just did in example A. Reflect the graph of y equal 4 to the x across the y-axis. So if you go back to example A, right, if we were graphing in 1/4 the x, well, let's put in the reflection, right, of 4 to the x across the y-axis. There's our graph of 4 to the negative x, right, which is the graph of 1/4 to the x. So I just want to show you that it is a decreasing model, and you see why these bases that are less than 1, why they decrease exponentially, even though the exponent was positive, right? If we rewrite it, right, we get that negative exponent. If I get rid of that fraction base, which I did by bringing up the denominator to numerator, by changing the sign, then we flip, we would change the sign of it. So you can see that there, those graphs there are the same. All right, let's do the last example. Now here's a different base. Right, here we got a base 3 exponential, example C. Now from that, we know that a base 3 exponential, its parent model, and this one has some changes. So I want to go ahead and talk about the parent graph. So f of x equal 3 to the x would be the parent of this model. So let's go ahead, while we have it, over here on the side, I'll go ahead and build in, right, a x and a y-axis. And let's put in the parent model. So 3 to the x power has a y-intercept at 0, 1, has a horizontal asymptote at y equal to 0, right? And it increases for all x, continuous, 1 to 1. Now, with that said, this is 3 to the x power. This is our basic a to the x graph, a being greater than 1, right? Base 3 exponential. Now, with that said, since we do have a different base than our previous examples, one thing I do want to make note of, you know these characteristics are the same, but you know graphically the graph's, again, a little different in shape as far as the curve and the increase in it. The greater the base, of course, the greater it'll increase. The sharper it has, again, the more bend this graph would have towards the y-axis. And the smaller the base would be the less the increase, right? So again, the greater the base, the greater it increases. But we know y-intercept, of course, is always 0, 1. We know the horizontal asymptotes at y equals 0. And maybe in a little bit we'll look at some together on our calculator to see it. Now I'm going to use that graph to get the graph that I want here in my parent model. And I'm going to graph this new one in red. Now we've got a couple changes to take care of. I've got a +1 and a -2. So let's go ahead and take care of this +1. So what does that ask us to do? Well, as we add 1 to x, that causes a horizontal shift left, right, 1 unit, because you're subtracting a -1 from x. x plus 1 is x minus negative 1. So we subtract 1 from every x coordinate, which will move it left 1 unit. So over here, as we're graphing this one, so 0, 1, for example, let's trace our point that we have plotted. It would move here to the point negative 1, 1, right, as we go left 1 unit. So I'm going to go ahead and plot that ordered pair. Right, negative 1, 1. That's true with every ordered pair. So right now our graph, if we were graphing in this exponential as subtracting 1, right, you can see our graph to the left 1 unit. That takes care of the horizontal shift. So there's the sketch right now of f of x equal to 3 to the x plus 1 power. Well, that's not it. So we have another change to apply, the minus 2. So what does the minus 2 do with our graph? Anytime we add or subtract a constant to our domain variable, it moves it left and right. We add or subtract a constant to our function, it moves it vertically. So now with a minus 2, we're going to go down 2 units on the y-axis. Now this is a key change in our graph. When I go a vertical shift, my asymptote also moves. So y equals 0, let's go down 2 units. That'd be at negative 2. Let's draw in the horizontal line. Now remember, this is an imaginary, I'm going to dash it in, horizontal line. But y equal negative 2 would be our horizontal asymptote, that vertical shift down 2 units. Now let's go ahead and move our point. So at left 1, let's go down 2. Down 1 would be at the point of negative 1, 0. Down 2 would be at the point here of negative 1, negative 1. So again, a vertical shift down 2 units will give us the point negative 1, negative 1. So graphically, yeah, we're still increasing for all x, right? And go ahead and graph in our function. There it is. There's our final piece. So we could erase everything else that we have up here at that point, right? We've got our parent model here in black, and you can see I dashed in the horizontal shift. And then I went down 2 units. That got me my point, negative 1, to plot. That got me my new horizontal asymptote at negative 2 because it was a 0. Now that's a key change because now that affects one of our key characteristics. Our domain, which is always all real numbers, and we can go ahead and write that in here. It did ask for the domain, the range. That's negative infinity to infinity. But our range is no longer that. What's the range of this graph? Right? The range is dependent on that horizontal asymptote, right? It's from negative 2 all the way to infinity. All y values greater than negative 2 would be our range. So again, the horizontal asymptote at negative 2, so our range is from negative 2 to infinity. And again, you can check these easily right on your calculator. So you want to look at them. Let's go to our TI. All right, we'll pull it up. So say we want to look at y equal to 3 to the x power, right? You want to graph in the exponential. There's our graph of 3 to the x power, right? As you're looking at the graph of 3 to the x, right? We can go here and look at its characteristics. You can go to your table. You can see again what happens when x is 0. You get an output of 1. 0, 1 is the y-intercept point. You can see from that graph. Now as you go to negative infinity, right, you see your horizontal asymptote. Look at your y value, closer and closer to 0. Now they never touch it. There is no x-intercept point, right? But you can see it increasing exponentially. Now let's go ahead and show these transformations. Now as I look at the graph of 3 to the x plus 1, what happens to my graph? Right, it shifts it. You now see it pushed to the left 1 unit. And let's go ahead and do our final change. What did we also have? We also had a minus 2, which we said was a vertical shift down 2 units. And now you can see your graph, which is flattening out. Look at your y values, like 1.99, right? It keeps getting closer and closer to negative 2 is where our horizontal asymptote is. So you can see those shifts. All right. You can also see, I wanted to show you an example, what happens to a base of like 1 over 3. Right? If you took 1 over 3 to the x power, right, it's going to be decreasing in value. Right? You notice that graph decreasing. It's a graph we had in blue of 3dx reflected across the y-axis. Now, again, that comes from the negative, right? If we were to put a negative exponent on 3 to the x, we would get that graph back. So again, those are nice things to look at with your grapher. Let's put in 3 to the negative x. And you see it overlaps it, right? You see your graph overlapping that one we had in red. Now we've graphed it there in that color of purple. That purple overlaps it. Now, of course, the greater the base, the more it increases. What if I graphed in 7 to the x power, comparing that to 3 to the x? Right, you can see your graph here increasing exponentially, right, at a greater rate, right? You can see it here in green. Here's our graph in blue of 3dx. Well, we got a sharper curve, still passing through 0, 1, still flattening out at the x-axis. So again, your calculator will give you a good picture of these exponentials. But again, that's a good review of our transformation properties too, as we're going through these exponential models.